Hi, thanks a lot for the introduction. I'm going to talk about a joint work with Jose Garre, Alberto Ruiz de Alarcon, Norbert Chu, David Perez Garcia, and Ignacio Sirac. So I like to think about tensor networks as some kind of puzzle where you're given small puzzle pieces out of which you can build a larger object. And all I'm trying to achieve is to understand how the properties of the big picture emerge from local properties of the puzzle pieces. All right, so I'm working with tensor networks, right? So my puzzle pieces are nothing but small rank tensors. And what I'm trying to build out of them is a state that lives in a large many-body Hilbert space. And what I'm trying to understand is some phenomena of this larger state, such as, for example, symmetries of the state, or when is it a topologically ordered state, or given that it has both topological order and symmetry, what can we tell about the structure of the tensor network? So let's start with the symmetries. So assume that our state has a symmetry on the form of some unitary to the nth power, such as, for example, spin flip, global spin flip. So it has been known for quite a while now that if you have an MPS that is symmetric under such a unitary, then under certain conditions of the tensor that I call injectivity, the tensor, the MPS tensor itself has this property that if you apply the unitary on the MPS tensor, then you can equally represent it as some invertible operator, and it's an inverse acting purely on the virtual level of your tensor. So why is this kind of result is actually important? So on the one hand, it's important because it gives you better algorithms. So people use tensor networks actually to really devise algorithms to solve many-body physics problems, meaning that they use it for as variational ansatz for finding ground states of Hamiltonians. And if the Hamiltonian happens to have such a symmetry, then you also know that the ground state has such a symmetry. And if you understand then the structure of the local building blocks, then you can write a better algorithm that respects the symmetry. And why is it going to be better? It's simply going to be better because if you understand this structure, then you know that some part of the tensor is just there to keep this symmetry structure, and actually the variational data is way smaller than what you have in the, like all the numbers that you have in the tensor. So answering these kind of questions, and so understanding the internal mechanism of symmetries is important on the one hand for devising better algorithms, and on the other hand, it also helps in theoretical investigations. So for example, exactly this result has been used to achieve the SPT classification in one-dimensional states. SPT stands for symmetric protected topological order. If you haven't never heard about it, don't worry. All right, so these kind of questions have been also studied in other settings. So people know also that in if you have a PEPS that is symmetric under such a global symmetry again, then under certain conditions of the PEPS tensor, you have a similar equation as before, namely if your physical symmetry applies on the tensor, then this tensor, then it's exactly the same as acting with some tensor product operators on the boundary of the tensor, in the virtual level of the tensor, in such a way that the operators facing each other will cancel when you contract the tensor network. All right, so my problem is that I want to apply this theorem for topologically ordered states. However, injectivity is in direct contradiction with topological order. So this brings me to the next topic, namely what is topological order and how to understand it from the local building blocks of your tensor networks. Uh, topologic topological order is a many-body phenomena. And even if you don't do many-body physics, you have seen already a topologically ordered state, namely the toric code. So it has many different properties that are very nice. I will grab exactly one that is easy to understand, and I think it will highlight the what the properties of the tensor are. Namely, that given a topologically ordered system, you actually have a number of locally indistinguishable states assigned to it. So for example, if you take your toric code and really put it on a torus, you have 4 locally indistinguishable states, the 4 code words that you have. Another interesting property of this ground state degeneracy is that not only that the states are locally indistinguishable, but also the number of degenerate ground states depends on the topology of your system. So for example, if you consider the surface code instead of the toric code with rough and smooth boundaries, you only have, I think, 2 indistinguishable states, whereas if you take your toric code and put it in a sphere, you will have only 1 ground state, or there will be no locally indistinguishable states. So it is known that the toric code, you can also represent it as a PEPs. And let's see what the symmetries of the models imply on the PEPs description. So the toric code is a stabilizer state, right? So if you take your stabilizer, this is a symmetry of your of the state. You can also concatenate together these stabilizers, and then you get a stabilizer, so a symmetry of your state that acts on a larger region. And if you take all the stabilizers in a given region, you will get a symmetry operator that acts on the boundary of the region, also known as Wilson loops. And this symmetry is exactly what can be represented in the tensor network. So if you work out the mathematics, what you will find that this symmetry will correspond to another symmetry on the tensor networks, namely a symmetry that acts only on the boundary. And in fact, this is not only true for extended regions, but already on the level of a single tensor. So when you write the toric code as a PEPs, what you will find is that this tensor is symmetric, and the symmetry is of the form that you have 4 X operators acting on the virtual degrees of freedom of the tensor. So I will think about this symmetry a bit of a different way. Namely, I will just put 2 of these x's on the other side, and I will imagine them to be part of a larger string of symmetry operators. And from now on, I will forget that these are just X operators. I will treat them as an abstract matrix product operator. So my statement is that these are exactly the symmetries of topologically ordered PEPs that are relevant for us. So let me just show that if you have such a symmetry, then you have such a symmetry also on an extended region. So it will be exactly this symmetry that I showed in this slide, okay? So for that, let's consider a large area and consider a symmetry operator acting on one side of the area. Now you can pick this tensor in the corner and use the symmetry condition to pull through the MPO, this tensor. And then you can pick the next tensor, pull through the MPO, and successively you can pull through all of the region, right? So this results in the fact that this extended region has the same type of symmetry as the local tensor. All right, so what I told you about is that one characteristic of topological order is that you have this locally indistinguishable states, the number of which depends on the topology of your system. So let me try to convince you that this arises exactly from the presence of these symmetries. So for that, let's consider our original PEPs, put it on a torus, And then let's consider another state that is essentially the same peps on the torus, except in an incontractable loop, we insert one of these symmetry operators. Now, if we consider these two states and we check on a region where you don't cross with the symmetry operator, then it's sort of plausible that these two states are the same on this region. But what happens if we check on a region that where the symmetry operator goes through? Well, the symmetry operator can move through the tensors, so I can just move it out of the region. Therefore, the two states are locally indistinguishable there as well. If you don't want to think about PEPs, by the way, this is exactly the pictures that you would draw on the toric code, okay? All right, so what I have told you so far is that toric code has a PEPs description. And this PEPs description has funny symmetries in forms of matrix product operators. And this symmetry is actually the origin of topological order. So there is a generalization of toric code called string net models that covers essentially all known non-chiral intrinsic topological order. So basically all topological order on lattice systems. These are models that are given in terms of a fusion category. And people know that they can be also written as tensor network states. So string net models you can represent as a PEPs. And it is also known that this PEPs has symmetries. And what kind of symmetries it has? Exactly the same as the toric code. It has these. It has MPOs that you can pull through the PEPs tensor without changing the tensor itself. By the way, in terms of the fusion category input of your string net model, so there are several different MPO tensors. So it's not simply just the X. So it's not a single MPO, but a bunch of MPOs that you can pull through the tensor. Namely, for each simple object in your fusion category, you can create such an MPO. All right. So what have we contributed to the field? So it was known already that string net models can be represented as PEPs, and they have these MPO symmetries. But as the string net models are usually formulated in terms of fusion categories, these symmetry operators are also formulated in some data of the category. However, we also note that fusion categories are just representations of certain algebras, namely Wyckoff algebras. And what we made is just the connection between Wyckoff algebras and these symmetry operators. And what we can do now is we understand the symmetries of these string net operators in terms of representations of some algebra. So when you see these matrix product operators, these are actually just representations of an algebra element. So by the way, this construction works because these algebras are created in such a way that you can define a tensor product representation. And as you can define tensor product representation, you can create tensor power of a given representation. And growing the number n here is the same as growing the size of the matrix product operator. All right, so now we come to our second result that we can characterize what happens if you have a topologically ordered PEPs and you have a symmetry on top of it. So this is just a reminder that if you had an injective PEPs with some global symmetries, then you could conclude that the symmetry operator acting on the PEPs tensor is the same as some invertible operators, the tensor product of some invertible operators acting on the virtual level. Sadly, injectivity is incompatible with the symmetries of the tensor. So the question arises, what happens if you have both the global symmetry and the topological order? And it turns out that we can answer this question in some special case. So it's not for all possible topological order, but for some special ones. And the answer is that when you apply the symmetry on your PEPS tensor, you can still pull it through to the virtual level. So you can equally represent this tensor as some operator acting on the virtual level. But this operator now will have also a matrix product operator structure. And what's characteristic to this matrix product operators structure is that when you pull through the tensor, it adds or removes the symmetry. All right. We also understand now how to generate these MPOs from some local algebraic structure. The bottom line is that it's related to some cohomology stuff. All right. So this brings me to the last topic, where we try to understand the boundaries of topologically ordered PEPs. So what we managed to understand is that we can create some kind of renormalization fixed point PEPs, which has the following funny property that if you take its transfer matrix, so this shows up when you try to calculate overlaps or expectation values of observables, then this sandwich actually has a hole in the middle. Okay, that is just to say that the transfer matrix has an exact MPO fixed point, okay? And this MPO, we also understand the structure that it can be built from the symmetries of your tensor times some local observables. And it turns out that this boundary MPO, it's actually a renormalization fixed point. Okay, so one has to think through what renormalization fixed point means in open systems. But if you take the appropriate definition, it just means that there is a channel that either duplicates your MPO tensor, and there is another channel that sort of shrinks back your system with one size. Okay, so now that we understood these boundary states, we can also ask the question how complex these boundary states are. And by complexity, what I mean is we try to understand how deep of a circuit of local channels you have to apply in order to construct it from the trivial, the tensor product state. So as it is a renormalization fixed point, very trivially, there is an upper bound, n. Namely, you can apply this channel that duplicates your MPS tensor. You can apply it one after the other. And if you think through, this is something that is not parallelizable. So it's actually an deep circuit. All right, can we do better? It turns out that for some cases, yes. Namely, we can create a depth-to circuit in some special cases. The way we do this depth-to circuit is that we create a channel that takes two MPOs and it glues them together to a larger MPO. This channel is local, so it only acts on these two middle particles, and it works independently of the system size. And we conjecture that out of, well, apart from these two cases that are enlisted here, it's actually, otherwise you would need a deep circuit. So the boundaries of PEPSs that don't fall into these two categories are actually difficult to create. This brings me to the conclusion. So I would try to convince you that topological order in PEPs arises from matrix product operator symmetries on the boundary. These matrix product operator symmetries are usually formulated in terms of fusion categorical objects, but fusion categories are just representations of some algebras, so you can equally think of these matrix product operators as the representations of some algebras. We have considered symmetries in PEPs that also has topological order, And we have found that symmetries in topologically ordered PEPs you can also represent with some kind of MPO on the boundary, where the MPO, when you pull it through the PEPs tensor, it adds or removes the symmetry. And finally, we started to understand how the boundary of topologically ordered PEPs looks like and how complex they are. And with this, I would like to thank you for listening.
Thank you very much, Andras. Are there any questions? If there are, please come up to the microphone. That's if there aren't, I really want to understand. Oh, is there? Sorry, I missed you.
So, do you have any idea what happened in renormalization fixed point?
No, sadly, not even for injective PEPs. I mean, it would be nice to be able to prove that the fixed point of your channel is always a matrix product operator, but it's actually very hard.
But if you can assume if the boundary state is MPO at least, but can you say something like it's approximately like a global part plus local part, or possibly quasi-local part?
I don't think there are any results like that. So what you would usually do is you try to repeat the same as in 1D. So you take your transfer matrix, you raise it to a power, and you try to converge, and then you want to see that it converges fast, and then you get an MPO. But this sadly doesn't work because of the presence of some Jordan blocks that can be exponentially large. So I don't know, sorry.
Okay, thank you.
Yeah, thank you for the talk. Can you say anything about non-injective PEPs, for example? Are there ways to detect whether a particular tensor network might be non-injective?
Yes, there are. So actually, you have to be a bit careful with that question because even for an injective tensor network state, you can create other description, so different tensors that is not injective. But if you want to detect, for example, the presence of these symmetries, the MPO symmetries, you can do it, and you can do it numerically. So there is Anna Franchus from our group who's doing that exactly.
Hi, thank you for your talk. So my question is, your work seems very much like a generalization of this whole G-injective PEP story from like a few years ago by Norbert Schuch and collaborators. What exactly is a generalization? How does it relate to these earlier G-injective stories?
So it so there are I also wrote some other citations. So so this pulling through condition and these MPOs are actually written down in this paper here. So basically, if you have a G-injective PEPs, then these MPOs are nothing but tensor products of the group elements. Okay.
Right.
Whereas if you have like a general string net model, this string net model is defined from some fusion category, from some data of the fusion category. And these MPOs you can also build from some data of the fusion category. If you want the exact construction, it's there. Yeah.
Okay, thank you.
Any more questions? If not, then let's thank the speaker again and go for a little break, 5 minutes.